हेलो फ्रेंड्स, तो राना एकेडमी में आपका स्वागत है। हमने स्टार्ट की है 11th क्लास की केमिस्ट्री की सीरीज एनसीईआरटी की। तो स्टार्ट करते हैं इक्विलिब्रियम। Chemical equilibria are important in numerous biological and environmental processes. For example, equilibria involving oxygen molecules and the protein hemoglobin play a crucial role in the transport of and delivery of O2 from our lungs to our muscles. Similar equilibria involving CO molecules and hemoglobin account for the toxicity of CO when a liquid evaporates in a closed container, molecules with relatively higher kinetic energy escape the liquid surface into the vapor phase, and number of liquid molecules from the vapor phase strike the liquid surface and are retained in the liquid phase. It gives rise to a constant vapor pressure because of an equilibrium in which the returning to liquid from the vapor. We say that the system has reached equilibrium state. At this stage, however, this is a non-static equilibrium, and there is a lot of activity at the boundary between the liquid and the vapor. Thus, at equilibrium, the rate of evaporation is equal to the rate of condensation. It may be represented by H2O, then gives the H2O vapor. The double half arrows indicate that the processes in both the directions are going to on simultaneously. The mixture of reactants and products and the equilibrium state is called the equilibrium mixture. Equilibrium can be established for both physical processes and chemical reactions. The reaction may be fast or slow depending on the experimental conditions and the nature of the reactants. When the reactants in a closed vessel at a particular temperature react to give products, the concentrations of the reactants keep on decreasing while those of products keeps on increasing for some time, after which there is no change in the concentration of either of the reactants or products. This stage of the system is the dynamics equilibrium, and the rates of the forward and reverse reactions become equal. It is due to this dynamic equilibrium stage that there is no change in the concentrations of various bases and the reaction mixture based on the extent to which the reactions proceeds to reach the state of chemical equilibrium. These may be classified in three groups. First, the reactions that proceed nearly to completion and only negligible concentrations of the reactants are left. In some cases, it may not be even possible to detect this experimentally. Second, the reactions in which only small amounts of products are formed and most of the reactants remain unchanged at equilibrium stage. Third, the reactions in which the concentrations of the reactants and products are comparable when the system is in equilibrium. The extent of the reaction in equilibrium varies with the experimental conditions, such as concentrations of reactants, temperature is very important in industry and laboratory, so that equilibrium is favorable in the direction of the desired product. Some important aspects of equilibrium involving physical and chemical processes are dealt in this unit, along with the equilibrium involving ions in aqueous solutions, which is called as ionic equilibrium. Equilibrium in physical processes. The characteristics of system at equilibrium are better understood if we examine some physical processes. The most familiar examples are phase transformation process, solid to liquid, liquid to gas, and the solid to gas. Solid liquid equilibrium, ice and water kept in perfectly insulated thermos flask, no exchange of heat between the needs contents and surroundings at 273 Kelvin, and the atmospheric pressure are in equilibrium state, and the system shows interesting characteristic features. We observed that the mass of ice and water do not change with time and the temperature remains constant. However, the equilibrium is not static. The intense activity can be noticed at the boundary between ice and water molecules from the liquid water collides against ice and adhere to it, and some molecules of ice escape into liquid phase. There is no change of mass of ice and water, as the rates of transfer of molecules from ice into water and reverse transfer from water into ice are equal at atmospheric pressure at and 273 Kelvin. It is obvious that ice and water are in equilibrium only at particular temperature and pressure for any pure substance. At atmospheric pressure, the temperature at which the solid and liquid phases are at equilibrium is called the normal melting point and or normal freezing point of the substance. The system here is in dynamic equilibrium, and enter we can infer the following: both the opposing processes occur simultaneously. Second, both the processes occur at the same rate, so that the amount of ice and water remains constant. Liquid vapor equilibrium. This equilibrium can be better understood if we consider the example of a transparent box carrying a huge tube with mercury manometer, a drying agent like and anhydrous calcium chloride or phosphorus pentaoxide is placed for a few hours in a box. After removing the drying agent by tilting the box on one side, a drying agent by tilting the box on one side, a which watch glass or a petri dish containing water is quickly placed inside the box. It will be observed that the mercury level in the right limb of the manometer slowly increases and finally attains a constant value. That is, the pressure inside the box increases and reaches a constant value. Also, the volume of water in the watch glass it decreases. Figure 7.1. Initially, there was no water vapor for an hour, very less inside the box. As water evaporated, the pressure in the box now increased due to addition of water molecules into the gaseous phase inside the box. The rate of evaporation is constant. However, the rate of increase in pressure decreases with time, and due to concentration of vapor into time water. Finally, it leads to an equilibrium condition when there is no net evaporation. This implies that the number of water molecules from the gaseous state into the liquid state also increases. Still, the equilibrium is attained. That is, rate of evaporation is equal to rate of condensation. H2O liquid, then it converts H2O vapor. At equilibrium, the gap pressure exerted by the water molecules at a given temperature remains constant and is called the equilibrium vapor pressure of water, or just vapor pressure of water. Vapor pressure of water increases with temperature. If the above experiment is repeated with methyl alcohol, acetone, and ether, it is observed that different liquids have different equilibrium vapor pressures at the same temperature, and the liquid which has highest higher vapor pressures more volatile and has a lower boiling point. If we expose three watch glasses containing separately 1 milliliter each of acetone, ethyl alcohol and water to atmosphere and repeat the experiment with different volumes of the liquids in a warmer room, it is observed that in all such cases the liquid eventually disappears, and the time taken for complete evaporation depends on first the nature of the liquid, second the amount of the liquid, and third temperature. When the washed glass is open to the atmosphere, the rate of evaporation remains constant, but the molecules are dispersed into large volume of the room. As a consequence of the rate of condensation from vapor to liquid state, which is much less than the rate of evaporation. These are open systems, and it is not possible to reach equilibrium in an open system. Water and water vapor are in equilibrium position at atmospheric pressure 1.013 bar and at 100 degrees Celsius. In a closed vessel, the boiling point of water is 100 degrees Celsius at 1.013 bar pressure. For any pure liquid at 1 atmospheric pressure, 1.013 bar, the temperature at which the liquid and vapors are at equilibrium is called normal boiling point of the liquid. Normal of the liquid, and the boiling point of the liquid depends on the atmospheric pressure. It depends on the altitude of the place. At high altitude the boiling point decreases. Solid vapor equilibrium. Let us now consider the systems where solids sublime. For vapor phase, if we place solid iodine in a closed vessel, after some time the vessel gets filled up with violet vapor, and the filled intensity of color increases with time. After a certain time, the intensity of color becomes constant, and at this stage equilibrium is attained. Hence solid iodine sublimes to glycoiodine on the vapor, and the iodine vapor condenses to give solid iodine. Now the equilibrium can be represented as solid iodine and vapor iodine. Other examples of showing this kind of equilibrium are camphor solid to camphor vapor, NH4Cl solid to NH4Cl vapor. Equilibrium involving dissolution of solid or gases in liquids, solids in liquids, gases in liquids, which states that the mass of a gas is dissolved in a given mass of a solvent at any temperature is proportional to the pressure of gas above the solvent. It can be generalized on that for solid to liquid equilibrium, there is only one temperature melting point at 1 atm 1.013 bar, at which the two phases can coexist. If there is no exchange of heat with the surroundings, the mass of the two phases remains constant. Second, for liquid to vapor equilibrium, the vapor pressure is constant at a given temperature. Third, for a dissolution of solids in liquids, the solubility is constant at a given temperature. Fourth, for a dissolution of gases in liquids, the concentration of a gas in liquid is proportional to the pressure concentration of the gas over the liquid. These observations are summarized in table 7.1. Table 7.1, some features of physical equilibrium processes: liquid to vapor, H2O liquid, and H2O gases, P H2O constant at given temperature. Solid to liquid, H2O solid to H2O liquid, melting point is fixed at constant pressure. Solute to solute, sugar to sugar solution, the concentration of solute is in solution is constant at a given temperature. Gas to gas aqueous, now gas aqueous per gas now is constant at a given temperature. CO2 gas and then gives in aqueous CO2. Now CO2 aqueous per CO2 gas is constant at a given temperature. General characteristics of equilibrium involving physical processes. For the physical processes discussed above, following characteristics are common to the system of at equilibrium. Equilibrium is possible only in a closed system at a given temperature. Both the opposing processes occur at the same rate, and there is a dynamic but a stable condition. All measurable properties of the system remain constant. The when equilibrium is attained for a physical process, it is characterized by constant value of one of its parameters at a given temperature. Table 7.1 lists such quantities. The magnitude of such quantities at any stage indicates the extent to which the physical processes has proceeds before reaching equilibrium. Equilibrium in chemical processes, dynamic equilibrium, A plus B then gives C plus D. 7.2 figure attainment of chemical equilibrium. Dynamic equilibrium or students activity. Equilibrium, whether in a physical or in a chemical system, is always a dynamic extreme nature. This can be demonstrated by the use of radioactive isotopes. This is not feasible in a school laboratory. However, this concept can be easily comprehended by performing the following activity. The activity can be performed in a group of 5 to 6 students. Take 200 milliliter measuring cylinders now marked as 1 and 2 and two glass tubes, each of 30 centimeter length. Diameter of the tubes may be same or different in this range of 3 to 5 millimeter. I fill nearly half of the measuring cylinder, one with the colored water. For this purpose, add crystal of potassium permanganate or to water and keep second cylinder number 2 empty. Put one tube in cylinder and second in cylinder second 2. Immerse of one tube in cylinder 1. Close its upper tip with the finger and transfer the colored water contains from in the its lower portion to cylinder 2. Using second tube kept in the second cylinder, transfer the colored water in a similar manner from cylinder 2 to cylinder 1. In this way, keep on transferring colored water uh, using the two glass tubes from cylinder 1 to 2 and from 2 to 1 till you notice that the level of colored water in both the cylinders become constant. If you continue trying enter transferring colored solution between the cylinders, there will not be any further change in the levels of colored water in two cylinders. If we take any analogy of level of colored water with concentration of reactants and products in the two cylinders, we can say the process of transfer which continues even after the consistency of two tubes of different diameters. We find that at equilibrium the levels of colored water in the two cylinders is different. How far diameters are responsible for change in levels in two cylinders. Empty cylinder 2 is an indicator of no product is at no product in it at the beginning. As figure 7.4 depiction of equilibrium for the reaction. Use of isotope deuterium in the formation of ammonia clearly indicates that chemical reactions reach a state of dynamic equilibrium in which the rates of forward and reverse reactions are equal and there is no net change in composition. In figure 7.5 chemical equilibrium in the reaction S2 plus I2 then gives S2 times S2 HI can be attained from either direction. Law of chemical equilibrium and equilibrium constant. equilibrium equation. Ke is equal to Cd upon Ab. Table 7.2, the initial and equilibrium concentrations of H2, I2 and HI. Table 7.3, expression involving the equilibrium concentration of reactants H2, I2, then give 2 times HI. At a given temperature, the product of concentration of the reaction products are raised to the respective stoichiometric coefficient in the best balanced chemical equation divided by the product of concentrations of the reactants raised to their individual stoichiometric coefficients has a constant value. And this is known as the equilibrium law and law of chemical equilibrium. Equilibrium constant for the reverse reaction is the inverse of the equilibrium constant for the reaction in the forward direction. Table 7.4, relations between equilibrium constant for a general reaction and its multiples. Problem 7.1, the following concentrations were obtained for the formation of NH3 from N2 and H2 at equilibrium at 500 Kelvin. N2 1.5 into 10 to the power minus 3 minus 3 m, H2 3 into 10 to the power minus 2 m, and the NH2 1.2 into 10 to the power minus 2 m. Calculate equilibrium constant. The equilibrium constant for the reaction N2 plus 3H2 and then gives 2 times NH2 can be written right as K is equal to NH3 G square upon NH2 N2 G into H2G whole cube. Problem 7.2, at equilibrium the concentrations of N2 3 into 10 to the power minus 3 m, O2 4.2 into 10 to the power minus 3 m, and INO 2.8 into 10 to the power minus 3 m. In a sealed vessel at 800 Kelvin, what will be Ke for the reaction? N2 gram plus O2 gram, then gives 2 times NO gram for solution. For the reaction equilibrium constant, Ke can be written as Ke is equal to NO whole square upon N2 into O2, then U is equal to 0.6022. Homogeneous equilibria. Equilibrium constant in gaseous system, PV is equal to nRT. Now table 7.5, equilibrium constants Kp for few selected reactions. Problem 7.3, PCl3, PCl2 and Cl2 are at equilibrium at 500 Kelvin and having concentration 1.59 molar. PCl3 1.59 mole and Cl2 and 1.41 mole PCl5. Calculate Ke for the reaction PCl5 and then gives PCl3 plus Cl2 solution. The equilibrium constant Ke for the above reaction can be written as Ke is equal to PCl3 Cl2 upon Cl5. Problem 7.4, the value of Ke is equal to 4.24 at 800 Kelvin for the reaction CO plus H2O, then use CO2 plus CH2 and gram. Calculate equilibrium concentration of CO2, H2, CO and H2O at 800 Kelvin if only CO and H2O are present initially at solution concentration of 0.10 mole each. Heterogeneous equilibria. Equilibrium in a system having more than one phase is called a heterogeneous equilibrium. The equilibrium between water vapor and liquid water in a closed container is an example of heterogeneous equilibria. H2O in a liquid phase then gives H2O in gaseous. In this example, there is a gas phase and a liquid phase. In the same way, equilibrium between the solid and its saturated solution CaOH 2 times solid and plus aqueous then gives Ca on the calcium and dipositive aqueous plus 2 times OH negative aqueous as a heterogeneous equilibrium. Heterogeneous equilibria often involve pure solids liquid. Now we can simplify equilibrium expressions for the heterogeneous equilibria. involving a pure liquid or a pure solid, as the molar concentration of a pure solid and or liquid is constant, that is independent of the amount of present. In other words, if the substance X is involved, then X solid and X liquid are constant. Whatever the amount of X is taken, contrary to this, X gases and X aqueous will vary as the amount of X is the given volume. Whereas let us take thermal dissociation of calcium carbonate, which is an interesting and important example of heterogeneous chemical equilibrium. CaCO3 solid, then in presence of heat, then gives CaO plus CO2 in gases. On the basis of the stoichiometric equation, we can write Ke is equal to CaO solid plus into CO2 gases and upon CaCO3 in solid. Units of equilibrium constant. The value of equilibrium constant K can be calculated by substituting the concentration terms in mole per liquid, mole per liter, and for Kp partial pressure is substituted and partial kPa bar or atom. This results in units of equilibrium constant based on molarity, or numerator and denominator are same for the same reactions. H2 gases plus I2 gases then gives 2 times HI, Ke and Kp have no units, N2O4 and then gives 2 times NO2 gases. Kp has a unit mole per Ke has unit mole per liter and Kp has no unit bar. Now equilibrium constants can also be expressed as dimensionless quantities if the standard state of reactants and products are specified. For a pure gas, the standard state is 1 bar. Therefore, a pressure standard Therefore, a pressure of 4 bar is standard state that can be expressed as 4 bar per 1 bar is equal to 4, which is a dimensionless number. Standard state C naught for a solute is a 1 molar solution, and all concentrations can be measured with respect to it. The numerical value of equilibrium constant depends on the standard state chosen. Thus, in this system, both Kp and Kec are dimensionless quantities but have different numerical value to different standard states. Problem 7.6. The value of Kp for the reaction CO2 gases plus carbon dioxide, carbon and solid, then gives 2 times CO in gases is 3 at 1000 Kelvin. If initially PCO2 is equal to 0.48 bar and PCO is equal to 0 bar and pure graphite is present. Calculate the equilibrium partial pressure of CO and CO2 solution for the reaction. Let X be the decrease in pressure of CO2, then CO2 plus C in solid, then gives 2 times CO in gases. Initial pressure is equal to 0.48 bar. At equilibrium, 0.48 minus X bar is 2X bar of Kp is equal to P square CO upon P CO2. No. X is equal to minus B plus minus B, under root B square plus minus 4AC upon 2A. The equilibrium partial pressure or PCO2 is equal to 2x is equal to 2 into 0.33 is equal to 0.66 bar. PCO2 is equal to 0.48 minus x is equal to 0.48 is minus 0.33 is equal to 0.15 bar. Applications of equilibrium constants. Expression for equilibrium constant is applicable only when concentrations of the reactants and products have attained a constant value at equilibrium state. The value of equilibrium constant is independent of initial concentrations of the reactants and products. Equilibrium constant is temperature dependent, having one unique value for a particular reaction represented by a balanced equation at a given temperature. The equilibrium constant for the reverse reaction is equal to the reverse of the equilibrium constant for the forward reaction. The equilibrium constant K for a reaction is related to the equilibrium constant of the corresponding reaction, whose equation is obtained by multiplying or dividing the equation for the original reaction or by a small integer. Let us consider applications of equilibrium constant to predict the extent of a reaction on the basis of its magnitude, predict the direction of the reaction, and calculate the equation concentration. In predicting the extent of a reaction, predicting the direction of the reaction, a reaction quotient Q. Figure 7.7, predicting the direction of the reaction. Q is smaller than Ke. Net reaction goes from left to right. QE is greater than Ke. The net reaction goes from right to left. QE is equal to Ke. No net reaction occurs. Calculating equilibrium concentration. Step 1, write the balanced equation for the reaction. Step 2, under the balanced equation, make a table that lists for each substance involved in the reaction the initial concentration, the change in concentration on going to equilibrium, and the equilibrium concentration. In constructing the table, define X as the concentration mole per liter of one of the substances that reacts on going to equilibrium. Then use the stoichiometry of the reaction to determine the concentration of the other substances in terms of X. Step 3, substitute the equilibrium concentration into the equilibrium equation for the reaction and solve for X. Now, if you are to solve the quadratic equation, choose the mathematical solution that makes chemical sense. Step 4, calculate the equilibrium concentration from the calculated value of X. Step 5, check your results by substituting them into the equilibrium equation. Relationship between equilibrium constant K, reactions quotient Q, and Gibbs energy G. Factors affecting equilibrium. Le-Chatelier principle. It states that change in any of the factors that determine the equilibrium conditions of a system will cause the system to change in such a manner so as to reduce or to counteract the effect of this change. This is applicable to all physical and chemical equilibria. We shall now be discussing factors which can influence the equilibrium. Effect of concentration change. The concentration state of an stress of an added reactant product is relieved by net reaction in the direction that consumes the added substance. The concentration stress of removed reactant product is relieved by net reaction in the direction that replenishes the removed substance. Or in other words, when the concentration of any of the reactants and products in the reaction of equilibrium is changed, the composition of the equilibrium mixture changes so as to minimize the effect of concentration changes. Let us take the reaction H2 plus I2 then gives 2 times HI. Figure 7.8, effect of addition of H2 on change of concentration for the reactants and products and the reaction H2 plus I2 then gives 2 times HI. Effect of concentration and experiment. Effect of pressure change, CO plus 3 times H2 then gives CH4 plus H2O. Effect of inert gas addition. Effect of temperature change. Effect of temperature and experiment. Effect of a catalyst, ionic equilibrium in solution, acids, bases, and salts, and Arrhenius concept of acids and bases, hydronium and hydroxyl ions, Hydrogen ion by itself is a bare proton with very small size of minus 10 to the power minus 15 meter radius and intense electric field binds itself with the water molecule at one of the two available lone pairs on it, giving H2O, H3O positive. Now, this species has been detected in many compounds. H2O, H2O positive, Cl negative. In the solid state, in aqueous solution, the hydronium ion is further hydrated to give species like H2, H5O2 negative, H2O3 positive, and H9O4 positive. Similarly, the hydroxyl ion is hydrated to give several ionic species like H3 now O2 negative and H3O2 positive, now H3O4 negative, etc. The Bronsted Lowry acids and bases, Lewis acids and bases, ionization of acids and bases. The stronger acid denotes a proton to the stronger base. Strong acids have very weak conjugative bases. The ionization constant of water and its ionic product. Ionic product of water Kw is equal to H positive plus OH negative. The pH scale. The figure 7.11 pH paper with 4 strips that may have different colors at the same phase, same pH. Figure table 7.5 the pH of some common substances. 7.11.3 ionization constants of weak acids. Ionization constants of some selected weak acids at 298 Kelvin. Table 7.6 hydrofluoric acid HF, nitrous acid HNO2, formic acid HCOOH, of niacin C5H4 NCOOH, acetic acid CH3 CH4COAH, the benzoic acid C6H3 H5COOH, hydrochloric acid hydrochloric acid HClO hydrocyanuric acid HCN, phenol H3 C6CH5OH. Ionization of weak base ionization constant. The equilibrium constant for base ionization is called base ionization constant and is represented as Kb. It can be expressed in terms of concentration in molarity of various species in equilibrium by the following equation. Kb is equal to m positive plus in bracket OH negative in upon MOH. The values of ionization constant of some weak bases at 298 Kelvin. The equilibrium constant for a net reaction obtained after adding two or more on the reactions equals the product of the equilibrium constants for individual reactions. Di and polybasic acids and di and polyacidic bases. Table 7.8 the ionization constants of some common polyprotic acids 298 Kelvin. Factors affecting acid strength. Size increases. HI is greater than HBr is greater than HCl is greater than HF. Electronegativity of A increases. HF is greater than here H2O is greater than NH3 is greater than CH4. Common ion effect in the ionization of acids and bases. Hydrolysis of salts and the pH of their solutions. Buffer solutions. The solutions which register change in pH on dilution or with the addition of small amounts of acid and alkali are called buffer solutions. Buffer solutions of known pH can be prepared from the knowledge of pKa. of the acid and pKb of base, and by controlling the ratio of the salt and acid, or the salt or base, the a mixture of acetic acid and sodium acetate acts as a buffer solution around pH 4.75, and a mixture of ammonium chloride and ammonium hydroxide acts as a buffer around pH 9.25. Or you will learn more about buffer solutions in higher classes. Designing buffer solution, preparation of acidic buffer. Henderson Hasselbalch equation. pH is equal to pKa plus log salt upon acid. Solubility equilibria of sparingly soluble salts. Solubility product constant. Table 7.9, the solubility product constant Ka of some common ionic salts Si on 298 Kelvin. Common ion effect on solubility of ionic salts. The equilibrium summary. When a number of molecules are leaving the liquid to vapor equals the number of molecules returning to the liquid from vapor, equilibrium is said to be attained and is dynamic in nature. Equilibrium can be established for both physical and chemical processes, and at this stage, rate of forward and reverse reactions are equal. Equilibrium constant K is expressed as the concentration of products divided by reactants, each term raised to the stoichiometric coefficient for reaction small a capital A plus small b capital B then gives small c capital C plus small d capital D. K is equal to C in power C, D in power D upon A power 2A, B power B. The equilibrium constant has constant value at a fixed temperature, and at this stage all the macroscopic properties such as concentration, pressure, etc. become constant. For a gaseous equation, equilibrium constant is expressed as Kp, as it is written by replacing concentration terms by partial pressures in Ke expression. The direction of reaction can be predicted by reaction quotient QE, which is equal to Ke at equilibrium. Le Chatelier's principle states that the change in any factor such as temperature, pressure, concentration, etc., will cause the equilibrium to shift in such a direction so as to reduce some factors such as temperature, concentration, pressure, catalyst, and inert gases on the direction of equilibrium, and to control the yield of products by controlling these factors. Catalyst does not affect the equilibrium composition of a reaction mixture, but increases the rate of chemical reaction by making available a new lower energy pathway for conversion of reactions to products and vice versa. All substances that conduct electricity in aqueous solutions are called electrolytes. Acids, bases, and salts are electrolytes, and the conduction of electricity by their aqueous solution is due to the anions and cations produced by the dissociation or ionization of electrolytes in aqueous solution. The strong electrolytes are completely dissociated a weak in weak electrolytes, there is equilibrium between the ions and unionized electrolytes. Molecules, according to Arrhenius, acids give hydrogen ions, while bases produce molecules. According to Arrhenius, acids give hydrogen ions, while bases produce hydroxyl ions in their aqueous solutions. Bronsted-Lowry, on the other hand, defined as acid as a proton donor and a base as a proton acceptor. When a Bronsted-Lowry acid reacts with the base, it produces its conjugate base and conjugate acid corresponding to the base with which it reacts. Thus, the Conjugate pair of acid base differs only by one proton. Lewis further generalized the definition of an acid as an electron pair acceptor and a base as an electron pair donor. The expressions of for ionization equilibrium constant of weak acids Ka and weak bases Kb are developed using Arrhenius definition. The degree of ionization and its dependence on concentration and common ion are discussed. The pH scale, pH is equal to minus log H positive, or the hydrogen ion concentration activity has been introduced and extended to other quantities. POH is equal to minus log KOH negative, and pKa is equal to minus log Ka, pKb is equal to minus log Kb, and pKw is equal to minus log Kw, etc. The ionization of water has been considered, and we note that the equation pH plus POH pKw is always satisfied. The salts of strong acid and weak base, weak acid and strong base, and weak acid and weak base undergo the hydrolysis in equation solution. And the definition of buffer solutions and their importance are discussed briefly. The solubility equilibrium of sparingly soluble salts is discussed, and the equilibrium constant is introduced as solubility product constant KSP. Now, its relationship with solubility of the salt is established. The conditions of precipitation of the salt from their solutions or their dissolutions in water are worked out. The role of common ion and the stability of sparingly soluble salts is also discussed. सो ये था इक्विलिब्रियम का वन शॉट वीडियो। यहाँ पर हमने सब टॉपिक्स थोड़े थोड़े करके कवर अप किए हैं, जिसमें आपको रिवीजन के लिए बहुत ज़्यादा बेनिफिट होगा। प्लीज़ इस वीडियो को लास्ट एंड तक ज़रूर देखिएगा। इस वीडियो में बहुत ज़्यादा इंपॉर्टेंट पॉइंट्स हैं। ये वीडियो थोड़ा लेंदी होगा। इस वीडियो में कुछ हमने स्किप किया है, तो वो प्लीज़ देख लीजिएगा। इक्विलिब्रियम हमारा 7th यूनिट है, जहाँ पर हमने पहले से देखा द इक्विलिब्रियम इन फिजिकल प्रोसेसेस, सॉलिड लिक्विड इक्विलिब्रियम, लिक्विड वेपर इक्विलिब्रियम, सॉलिड वेपर इक्विलिब्रियम, इक्विलिब्रियम इन्वॉल्विंग डायसोल्यूशन ऑफ सॉलिड और gases in liquids, some features of physical equilibrium, general characteristics equilibria involving physical processes, equilibrium in chemical processes, dynamic equilibrium student activity, a law of chemical equilibrium and equilibrium constant, initial and equilibrium concentrations of H2, I2 and HI, expression involving the equilibrium concentration of reactants H2, I2 and 2 times HI, relations between equilibrium constants for general reactions and its multiple, homogeneous equilibrium constant in gaseous systems, equilibrium constant Kp for a few selected reactions, heterogeneous equilibria, units of equilibrium constant, applications of equilibrium constants, predicting the extent of reaction, predicting the direction of the reaction, calculating equilibrium concentration, relationship between equilibrium constant K, a reaction quotient Q, and K Gibbs energy G, factors affecting equilibria, effect of concentration change, effect of concentration and experiment, effect of pressure change, effect of inert gas addition, effect of temperature change, effect of temperature and experiment, effect of catalyst, ionic equilibrium in solution, acids, bases and salts, Arrhenius concept of acids and bases, hydronium and hydroxyl ions, the Bronsted-Lowry acids and bases, Lewis acids and bases, ionization of acids and bases, the ionization constant of water and its ionic products, the pH scale, ionization constants of weak acids, the ionization constants of some selected weak acids, Ionization of weak bases. The values of ionization constant of some weak bases at 298 Kelvin. Di and polybasic acids and di and polyacidic bases. Factors affecting acid strength. Common ion effect in the ionization of acids and bases. Hydrolysis of salts and the pH of their solutions. Buffer solutions. Designing buffer solutions. Solubility equilibrium of sparingly soluble salts. Solubility product constant. Common ion effect on solubility of ionic salts. देन समरी. तो इक्विलिब्रियम में हमने ये सब देखा पहले से. प्लीज़ इस वीडियो को ज़्यादा से ज़्यादा शेयर कीजिएगा क्योंकि आपके रिवीजन में बेनिफिशियल होगा. इस वीडियो में हमने पहले से देखा, कुछ इंपॉर्टेंट पॉइंट्स देखे, इक्विलिब्रियम का स्टेट देखी, इक्विलिब्रियम मिक्सचर देखा, डायनेमिक इक्विलिब्रियम देखा. तो ये सब हमने देखे. So thank you so much for watching. Please like, share and subscribe.